We've just spent 2 weeks in the notational salt mines learning all of this notation to allow our objects of the class types that we write to be fully fledged first-class citizens of the world, to have their own identities, and to choose how the world can interact with them. So I have my class rectangle. And we'll see it's even present in this file here. We're not done with it yet. And we've seen over the past couple of weeks that we can define how a rectangle is created, how it's destroyed, and how it interacts with the outside world. We've even seen near the end of last week the idea of rectangle's conception of itself, that it can now shout to the world, "I am rectangle." And it can present this abstraction. But now we have to begin considering if rectangle is a fully fledged citizen of the world, maybe there are other members of its family. So maybe one day it discovers that it has a sibling. For example, a circle. Or maybe one day it meets its long-lost child, a square. And if we think about this, if we design all of these objects that present a particular abstraction, maybe we discover that there are groups of objects that sort of present similar abstractions. Because you could argue there are things you might want to do with rectangles and there are things you might want to do with circles, and those might be separate. There are times you just need a rectangle. But there are also times when both a rectangle and a circle might be relevant for the same task. In fact, they might discover that although they are estranged, they are members of the shape family. And so the main topic for this week is another way of attacking that question of how do we achieve the perfect abstraction. And it has to do with the idea of specialization. And I think this is a concept, the one that we're going to unfold over the week, that in a sense is one of the defining characteristics of object-oriented programming. In a certain way, we are sort of reaching the summit of the mountain as far as object-oriented programming languages go. We're not at the summit of the mountain of C++. That mountain is basically vertical and just goes up past the clouds. But as far as object-oriented programming that you might see in a variety of language, this feature that we're getting at this week, which can be referred to in a variety of ways. So we'll use the term subclasses. We will definitely use the term inheritance. This feature is sort of a defining characteristic of object-oriented programming. All right, so before we get too far into the clouds, let's talk about some stuff that looks a bit familiar. Here we have our point class, and the point class has had the chance to grow with us over the past little while. Here is the version we'll work with for now, so it's been pruned down a little bit since last week. We're done with all of the ridiculous variations that we saw in the later videos of last week's material. And down here, I've got this week's version of the rectangle class, all refreshed and ready for another week of being a rectangle. We've got our private default constructor as before. Just like in most of the videos from last week, the rectangle is choosing to represent itself internally, although you might not be able to tell from outside, by 2 points, lower left and upper right. Okay, there they are. And if you want to know the width or height, it's able to retrieve those using those 2 points. When I want to construct the rectangle, I can provide the 2 points directly. So we could call these 2 points. Lower left is x0, y0, and upper right is x1, y1. So I've changed the notation a little bit since last week, just to try and standardize things for the examples for this week. Okay, so I can construct a rectangle by giving those parameters. And then I've also added this feature where the rectangle can tell you its own name. And hopefully you stare at that and think that seems a little bit unnecessary, because if I have a variable of type rectangle, I damn well know that it's a rectangle. Just bear with me here, I get that it's contrived, although it turns out that this is actually surprising, despite being contrived, is surprisingly common in practice for objects to be able to reflexively tell you their own name. The same way that even though I call myself I or me in my head, I will grudgingly tell you, "Hi, I'm Bill," if I have to introduce myself somewhere. And then I've got the familiar getWidth, getHeight, and getArea functions, which use the internal data of the rectangle, data that you're not allowed to understand from the outside. It uses that internal data to compute those parameters, so width, height, and area. Okay, but down here, I've defined a square. And what I want to illustrate right now is that the square has some eerie similarities to rectangle, even though class square is distinct from class rectangle. And given that we have type safety in C++, the way that this code is written, a square and a rectangle are 2 completely different things, just as different as int and rectangle, or int and a pointer to std pair or something. Just 2 completely different types that happen to have some eerie coincidental similarities. Okay, so the constructor constructor that I've written for a square takes a point in the plane somewhere. So I'll try and draw this. This is going to be a bit of a, these next few shapes are going to be a bit difficult. So there's an attempt at a square. It's a little bit concave looking. You might need to get that checked out. I have this square here. I could define a square by simply providing you with a single corner of the square. Let's say I provide you with the lower left corner, and then I provide you with the side length. And the idea is that because all four sides of the square, even though my freehand drawing isn't very good, all four sides of the square are the same, all I need to do is provide you the side length. But interestingly, if you stare at it, you'll realize that the square is representing as an abstraction that it takes a single point and a side length, but deep down what it's actually storing, if you look at what the constructor is really doing, the square is apparently storing itself the same way a rectangle would be. Another way of illustrating the similarities there, the sort of familial resemblance of a square and a rectangle. Internally, the square is representing itself by a lower left and upper right corner. It just constructs the lower left corner to be the point you gave, and the upper right corner to be the point you gave plus the side length. So just adjusting for the side length, which is the same on all four sides. There's the destructor for a square, and then the square can also tell you its name. Notice, this is the exact same function signature I had inside the rectangle class. And just like in the rectangle, I can get the width, I can get the height, and I can get the area. And in fact, the calculation is identical. And hopefully already you can recall from deep down, way back in the C language, if you find yourself writing identical code in multiple places, maybe you need some more modularity. So remember, way back to the second or third week of 111, if I find myself copying and pasting code, what I need is a function. Well, I have a function here, so that's not going to fix that. But there's something a little bit off about this. We shouldn't have this level of duplication. And then in the private data for the square class, we've got lower left and upper right, just like the rectangle. And again, it looks a lot like the square is the long-lost child of the rectangle object. It has so much in common, so much of a resemblance, and so much of its behavior is identical to that of a rectangle. It's just a special kind of rectangle. Okay, but then down here I've got a circle. So a circle is definitely not a square or rectangle, and you can pause the video and go look that up if you don't believe me. So a circle is not a square or rectangle, and now I've got to attempt to draw a circle freehand on the screen. Well, that's about as good as we're going to do. That's pretty damn good, I think, right? I guess I have low standards, but that's pretty damn good. I can represent my circle, to the extent we believe this is a circle. I can represent my circle, I think, by storing a single point, which is the center point of the circle. We'll say CX and CY, and then the radius. If you give me those two things, I can produce a circle. I'm not saying I can draw the circle, as you can see, but I can at least conceptualize. In my imagination, the circle looks pretty good. So my circle constructor, I've got a private default constructor like before. It just sets the radius and center point to be 0, so we get this degenerate case. If you provide a center point and a radius, it initializes them accordingly. So there's the radius being initialized, there's the center point, and there's a destructor. And then I have provided exactly the same four functions that I provided for the square and rectangle. But of course they're different because, the circle's name is circle. I guess that part's obvious. The width of a circle, well, I'll assume, regardless of exactly how you align the circle, I assume you mean by width the diameter. So that's 2 times the radius. Same with the height. That is not the same calculation used by square and rectangle for lots of different reasons. The biggest one being that circles and rectangles are different. But also because the circle isn't storing itself in terms of 2 points like the rectangle is. And then to get the area, I return pi r squared, which again, you can go look that up, but that is the correct formula, I claim. I should make a note. So I've included at the very top of my file, we'll scroll all the way up, the header numbers. And this is a case of going fishing in the standard library for something. But to be clear, if you want to use the value of pi in C++20, it was actually surprisingly annoying to use the value of pi before C++20, or there was a gap between standards where the value of pi was hard to retrieve. If you want it, you can get the constant out of this std numbers library. So you go into std, then into numbers, then you get the value pi. And so that's where this came from. And it's in the header numbers. And it's one of those things you don't need to memorize because obviously if you ever need that, you could look it up. And then the circle class stores its radius and its center point. Okay, so what I have here are three different shapes that in the eyes of the language right now, class circle, class square, class rectangle, are completely different. The same way that circle is different from a vector of int. They're just two different types. The language has no way of maybe, I don't know, catching the same suspicions that you have about the similarities between these things, because they are semantic similarities. Two different types can have a function with the same name. That doesn't mean anything to the compiler, right? The string type has a function called size, and the vector type and the list type have functions called size. They all might mean different things, although I guess they're similar in their meaning, but you could define your own type with a function called size that would have some completely different meaning altogether. And so the compiler doesn't care if two different types have member functions with the same name. It doesn't infer from that that they are similar types. But we look at this. We say these are all representing shapes. These are similar. They have similarities that I guess aren't captured by the fact that we just have a bunch of separate types. And that is going to be our quest this week, is to find some way of representing those similarities in an orderly fashion that allows us to, I guess, take advantage of the fact that circles and rectangles do have a lot in common, and certainly allows us to deal with this situation where the squares, get height, get width, get area functions appear to be identical to those of the rectangle. Okay, so what I have to demonstrate that right now is at least one example of how these similarities can result. Although the types are similar, the language doesn't know that they're similar, and that produces a strange form of duplication that we should by now recognize as something that we want to avoid. So suppose I want to print out circles, rectangles, and squares, and I, the programmer, know that they are similar, and therefore I want to print them all out with a consistent representation. So what I have on lines 127, 135, and 142 are three copies of a function print shape. And we've seen over the course of the semester, there are occasionally times in C++ where you find yourself writing several functions with the same name and exactly the same contents, but different argument types or a different return type. And there are a few ways to address that. This week, in the case of several types that are similar to each other in function, in purpose, that we are writing ourselves, that are members of the same family, there's one remedy, which is subclassing or inheritance, this specialization idea. There's also the other situation, I guess a more pragmatic case, where you might have remembered earlier in the semester, if we want to print out a list or print out a vector, two types that are similar in some ways, but the language defines to be fully distinct, there are remedies to that as well. We'll talk about those next week. So there are two ways we could go. This week, we're going to talk about this idea of defining rectangle and square to be deliberately similar, and then using that to allow only one function to be needed. But this is definitely duplication we want to avoid. All right, and down in main, I construct a rectangle, then a square, then a circle, and then I just print them all out to show that from the point of view of a programmer, even with this duplication, if I play my cards right, I can present to the programmer of main this abstraction that to print out a shape, you just call the print shape function. So a programmer in main might think, hey, yeah, a rectangle, a square, and a circle, they're all shapes, and I can treat them the same way. I can print them out like any other shape. That is what we want to achieve. In this example, we are achieving that in a sort of roundabout way. The person implementing print shape had to do a lot of extra work, a lot of redundant work, but they were able to present to the programmer of main the abstraction that square, rectangle, and circle really are peas in the same pod. They're sides of the same coin. They're members of the same family. And we just want some way of codifying that in the language so we don't go around copying and pasting print shape functions, that we get the flexibility that comes with being able to explicitly indicate that two classes are similar or that one is a specialization of another. So we'll run this and we can prove that sure enough, I mean, we get the usual spam of printing out when the constructors are being called. We're going to need that later in the week. We're not done with that yet. And then we print out. The shape rectangle has width, height, and area 2, 3, and 6, respectively. The square has this width, this height, and this area. There's the width, height, and area of the circle. And we'll take a look again at print shape. And because the shape can tell you its own name, we notice that to print out a square, a rectangle, and a circle, we are using identical code. Wouldn't it be great if I only needed one implementation of print shape to do this, to acknowledge that really what I'm dealing with are three special cases of a much more general concept. Rectangle, square, and circle are all just shapes. And in fact, square is just a rectangle, which in turn is just a shape. We want some way of formalizing that in our language.